everybody, thank you for stopping by my video. My name is Patricia from the University of Maryland at College Park, and today I'm going to talk to you about hygroscopicity measurements and analytical methods of atmospheric soluble sugars. So first of all, to start, I just wanted you to know that this presentation is based on our recently published paper titled The Direct Comparison of the Submicron Aerosol Hygroscopicity of Water-Soluble Sugars. This was published in November in the ACS Earth and Space Chemistry Journal. If you're interested to read more on this paper, you can go ahead and scan this QR code and it'll take you straight to that paper. So let's get started. Aerosol particles are liquid or solid particles suspended in the atmosphere. And although they're tiny, their size only from several nanometers up to several microns, they do have quite an impact on human quality of life. They can affect the biogeochemical cycles. They also have various health effects. And what I'll be focusing on today are the climate effects of aerosol particles, specifically what we refer to as the indirect effect of aerosols. So the indirect effect of aerosols happen when particles in the atmosphere can uptake water and actually form droplets or clouds. These droplets can in turn scatter or absorb radiation, leading to a cooling or heating effect on the atmosphere. However, the magnitude of this indirect effect on the total radiative budget of the planet is still rather uncertain. As you can see from this chart here by the Intergovernmental Panel for Climate Change, it shows that the indirect effect of aerosols do have a generally net cooling effect on the atmosphere, but it is associated with a rather large error bar. And therefore, there is a need for scientists to contribute to this body of knowledge that's dedicated to reducing the radiative forcing uncertainty due to the aerosol indirect effect. And that's where our research comes in. So we contribute to this cause by measuring the hygroscopicity or water uptake of atmospherically relevant aerosol particles at a broad range of saturation. So this can range from subsaturated all the way to supersaturated conditions. And we want to understand the cloud formation and water uptake properties. So we focus on water-soluble organic compounds. Specifically, we'll be looking at 4 single component systems, and we'll be analyzing and studying their water uptake using 3 different methods. So let's get to know our system. We focused on atmospherically relevant saccharides or sugars. The first one is a well-studied saccharide, which is levoglucosan. This is often used as a marker for biomass burning. We also look at sucrose, which is another atmospheric aerosol that's present and is usually used as a model for glassy or viscous particles. Third is trehalose. This is usually used as a marker for biogenic secondary organic aerosols. And lastly, we picked raffinose, which is less atmospherically relevant, but it does have a larger molecular weight for us to compare our others. So what do we really do in our lab? How do we take these water uptake measurements? So I like to break it down into 3 phases. The first one is aerosol generation. So we start with an aqueous solution that's dilute, and we atomize that using a constant output atomizer, and we dry it. And that way we get this stream of dry aerosol particles. And from there, we split the stream into 3 ways, and all of them go through a differential mobility analyzer for size selection. And the third phase, which is the most important phase in this experiment, are the water uptake measurements. We use 3 different instruments. The first one is the cloud condensation nuclei counter, and we also use a humidified tandem differential mobility analyzer, as well as a cavity ring gas spectrometer. Now, using these 3 instruments combined, we are able to measure water uptake at supersaturated conditions using the CCNC and subsaturated conditions using the HTDMA and the CRDS. Now let's talk about our results. The first one is from our supersaturated water uptake measurements, or the cloud condensation nuclei counter measurements. We get this parameter called the dp50, also known as the activation diameter. This is just the dry diameter of a particle at which half the population is able to form droplets at a given supersaturation. And we can illustrate that here as a graph of the ratio between droplets and total particle count as a function of the dry mobility diameter. And we get this sigmoid curve, and from there you can easily find the activation diameter. So each of these curves represent a single supersaturation condition. So to get a graph like this, we were able to measure water uptake at 6 different supersaturations. Next is for the humidified tandem differential mobility analysis, or HTDMA. From here we get a parameter that's called a growth factor, or geometric growth factor. To get the growth factor, we need to find the dry diameter, which is the size selected particle mobility diameter. And we also need the size distribution of the humidified particles that will give us the wet diameter. And the ratio of these two diameters give us the geometrical growth factor. So we can plot that in a chart like this. This is the wet mobility diameter as a function of dry diameter, and the slope will give you the growth factor of your system. So our sugars here are shown in purple, red, blue, and dark green. And we also plotted ammonium sulfate in light green here, just for a comparison, because it is an atmospherically prevalent and highly hygroscopic salt in our atmosphere. So we can see here that our sugars tend to be quite a bit lower in terms of growth compared to inorganic particles, such as ammonium sulfate. So lastly, our results from our cavity ring mass spectroscopy. From this, we get what's called an optical growth factor. So it's similar to the geometric growth factor from the HTDMA. It is also a ratio, but instead of diameters, it's a ratio of extinction coefficients. As you can see here, the optical diameter is a ratio of the humidified particles extinction coefficient to the dry. So we can plot our optical growth factor as a function of dry particle diameter. I picked sucrose to show here at about 86% relative humidity, and we can see the uncertainties and the trend of our FRH with dry particle set. So with these three instruments, we get 3 different parameters. However, we are able to kind of intercompare them by using the single hygroscopicity parameter kappa. So for the dp50, or activation diameter, we can easily retrieve kappa using this equation that's based in Kohler theory. Similarly, with the geometric growth factor, we can just retrieve it through this equation. However, the conversion from FRH to kappa is less commonly done. So for the first time, as far as we're aware, we will be comparing 2 different retrieval methods for kappa from FRH. This first one here is based on me theory, and the second one is based on an empirical correlation. So let's jump to our compiled results and compare what we got. So what I like to point out here is this is just a plot of the kappa values as a function of each system. And we have our ideal kappa or theoretical kappa as the dashed lines, and our different kappa values from different measurement methods as the symbols. So what we see first here is that there's only a small deviation between ideal kappa, the CCNC kappa, which is the black circles, and the HTDMA kappa, which are the red squares. Additionally, the FRH derived kappa values from me theory and empirical formulas, right there, the diamonds here, they're fairly comparable at the selected sizes. And we also notice that the FRH kappas, or the cavity ring down kappas are consistently higher than the ideal CCNC and HCDMA kappas. This is most likely due to how sensitive our CRDS is to relative humidity fluctuations, as well as to the presence of doubly charged particles. We also were able to provide the first kappa HCDMA values for raffinose and trehalose. And again, if you'd like to know more about what we did in this paper, you can go ahead and scan the QR code and I'll take you right to that paper. We also considered the effects of limited solubility, but what we saw were our results were pretty close to ideal and fully deliquesced aerosols. Lastly, we did observe a molecular weight dependence of our kappa values, where kappa values decrease as the molecular weight of the compounds increase. So just to summarize everything through this work, we were able to add to the database of WSOC droplet growth measurement work, and we obtained novel values for HCDMA, kappa of raffinose and trehalose. We were able to compare 3 different methods for water uptake measurements using the cavity ring down spectroscopy, HCDMA, and CCNC. Therefore, we were able to compare sub and supersaturated kappa values. And we were also able to compare the kappa values that resulted from geometric and optical methods. We're also able to compare empirical and mean-theory-based kappa value retrieval from optical growth factors. And we showed a molecular weight dependence of saccharide WSOC kappa values. So to tie everything all up, I think from this work, we were able to improve our understanding of saccharide hygroscopicity at sub and supersaturated regimes. And we were also able to improve our understanding of the water uptake behavior of non-surface active WSOCs in our atmosphere. And to end this presentation, I'd like to acknowledge my advisor, Dr. Akuya Asaoku, as well as my fellow lab members. Also, our collaborators at Bucknell University and Penn State University. I'd also like to thank AMS for giving me this platform to talk about my research today. And I'd also like to acknowledge the source of our funding, which is the NSF. And if you have any questions or any interest in all this, please feel free to contact me. I have my email as well as my LinkedIn, and this link will lead you to the website of our laboratory if you want to learn about our other projects as well. So that brings me to the end of my presentation, and I hope you enjoy the rest of your conference. Bye.